Hello, this is part 2 of section 2.5, which is about continuity of a composite function. This is very, very important concept for continuity, since we have a function inside another function. Okay, so we have to ensure some conditions to make this composition works well for continuity. In fact, if we have a limit of, if we want to do the composition f composite with j, so we must have limit of g of x when x approaches a is equal to b, and then study the continuity of f of gx at the point b that we obtain. Okay, so for example, simple example of composition is like that. When you have, let's say, f of x is equal to square root of x cubed plus 1. So we can make this composition like, let me call this h better. Okay, so h of x is equal to that. Then I will choose f of x equal to root x, and g of x is equal to x cubed plus 1, so that h of x is equal to f composite with the g of x. Okay, so this is the composition. If I want to study the limit of h of x when x approaches 1, that means it's like you start by g of x when x approaches 1. So you do like that, limit g of x, x approaches 1. This is a simple example just to understand the concept of composition. So it will be equal when we replace g of x, it is equal to 2. Then I will go to f and study in the limit in this point. So limit f of x when x approaches 2 is equal to root 2. And mainly we find the limit if we do it directly on the function h of x when x approaches 1, you will find the root of 2, and this is exactly what we found with the composition. So here, of course, is a simple example to understand the concept of composition of function. More interestingly, we will see how to obtain the continuity of composite function. Okay, so if we have the limit, then we have the same thing for continuity. If g is continuous at a, f is continuous at g of a, then the composition f composite of g is continuous at a. And here the order of composition is important. You remember that f composite with g is not the same as g composite with f. Okay, so let's see an example here. Look at this function, and we want to say where these functions are continuous. So just we give here the composition of our function, h of x is equal to sine x squared. So I will choose f and g. So f is the first function, it is sine what it is inside, so sine x. And g of x is x squared. So clearly here you see that the composition makes sense for h. Okay, now since this function j is continuous everywhere, so on R, okay, and this one is also continuous on R. So from the theorem of composition, f is continuous on R. Okay, I will use sometimes to gain some time the continuity like that, continuous. Okay, now this is in fact a simple example, but if we want to learn more about the continuity of composition, we will see this function here, which is a little bit more complicated than the first one. So here I will choose my small f is ln of x, and g of x is 1 plus cosine x. And in fact, here the continuity is somehow related to the domain of the function. So we want to make sense to this expression, capital F of x. What we should have, in general, let me recall you something. If you have h of x equal to f composite with g of x, to make sense to this definition, if we have the following: 1, take x in domain of G, that will give you a condition, write it. 2, compute the range of G, and range of G must be included in the domain of F. Then you will find second condition here. Okay, so 1 and 2 will make sense to the definition of H. 1 intersection with 2, this will give the domain of the composite function H. Okay, so that's remember that. And if you have the domain, then the function, since it is basic function formed by composition of basic function, then so the domain of continuity is the same as domain of definition. So let me apply this strategy here to this function. So I will say that f of x is equal to ln x, g of x is 1 plus cosine x. Now what is the domain of g? This is number 1. Domain of g is equal to r, all real number. So what is the range of g? Range of g, this is from semester 2. You remember, cosine is all the time between -1 and 1. So we shift by 1, it will give 0, 2. Now I need that this range must be included in the domain of f, small f. What is the domain of small f? This is logarithm function, so it is 0, infinity. I need that 0, 2 included to 0, infinity. This is not possible unless we remove this closure for 0, make it open. So what in the range of g that makes the g of x equal to 0? So we have to remove all the x such that g of x is equal to 0. And now the question, when g of x is equal to 0? This will give an equation, trigonometric equation, 1 plus cosine x equal to 0. And from our trigonometric course, we can find all the solution of these equations. So in the next step, I will solve this. Remember what we have here. Then I will find the domain of definition. So 1 plus cosine x equal to 0. That means cosine x is equal to -1. And when 1 cosine is equal to -1, it's at the angle pi plus 2k pi. So this gives that x is equal to pi plus 2k pi. All these points satisfy 1 plus cosine equal to 0. So I have to remove these from all the real number that we from all the real numbers that we can take. So if I remove this, I will get that 1 plus cosine is between 0 open and 2, which is fine for my my domain of composite function. So the domain of the capital F function is, in fact, all real number except this point pi plus 2k pi with k in z. And by our theorem in the course, also the function is continuous on this domain, since it is formed by composition of two continuous functions on D of f. Okay, so that's for this example, and here you will see the solution in the slides. Here it is. And then we have the last part of this lecture, which is the intermediate value theorem. In short, we will call it IVT. Okay, so what is the IVT? This is application of the continuity. If we don't have continuity, then no IVT. The IVT says that if you have a continuous function on a closed interval AB, and we take a number n between the two values f of a, f of b. We don't know which one is bigger from the numbers f of a and f of b, so it's a comparison. The most important that the number n is between them, whatever which one is bigger here. The most important that they don't equal each other. Then we are certain that there is a number c in the open interval AB such that f of c is equal to n. If we want to understand this, look at this graph of function f of x. Take 2 points a and b. Okay, f of a is here, f of b is somewhere here. Okay, so what the IVT says, if you take a number here n, you are certain that you will find a point on the graph such that f of c is equal to n. That's the IVT. Okay. And here you see the situation for the two graphs where we applied here the IVT theorem. Okay. Let's take a simple corollary of the IVT is that when we have f of a and f of b of different sign, it means one positive, another is negative, then as a simple application, as particular case, we can take the n equal to 0 in the previous theorem. Then we can conclude that there is c in the open AB such that f of c is equal to 0. And this corollary is sometimes much used because in general we will look to the roots of the function. So we will use, instead of the original IVT, we will use the corollary number 6. Okay, so look at this example here. We want to show that the equation, the following equation, has a root between 1 and 2. We don't want to find the root. We just show that there is at least a root. By the way, the IVT gives at least one root. We may have many roots for the equations, but at least one is guaranteed by the IVT. Here we have our function. Let's call this f of x. Clearly, this is continuous function. Don't forget the continuity in the IVT. So this is continuous function on all real numbers. So in particular on the interval, the closed interval 1, 2. Then I will compute f of 1. F of 1 is 4 minus 6 plus 3 minus 2. So I will have 7 minus 8, that means minus 1, which is negative. And f of 2, we can compute this. It's something positive. Let's say 32 minus 24 plus 6 and minus 2. So clearly here it's a positive number. Okay, so we can apply the IVT, and we certainly have at least one root between 1 and 2. There exists C such that f of C is equal to 0. That's the IVT. Okay, that means the root of f. Here is the solution. More details. Okay, so we have these two conditions. We have the continuity, not forget that. And then we conclude that there is a C between 1 and 2 such that f of C is equal to 0. Now we will end this lecture by the try and check examples. So we want to show that the equation ln x equal to x minus root x has a root between 2 and 3. Usually, if you have equation like that, transform it to the left, then this is equivalent to say that I want to get ln x minus x plus root x equal to 0. And take this your function f of x. Now you will compute, this is continuous function on its domain of definition, which is 0, infinity. So in particular, it is continuous on 2, 3 closed, the desired interval here to 3. Okay, so that's one step. The other step is to compute f of 2 and f of 3. Okay, so f of 2 is equal to ln 2 minus 2 minus root 2, which is clearly negative, and f of 3 ln 3 minus 3 minus plus here, sorry, so I have to repeat here. So ln 2 minus 2 plus root 2, this will be, sorry, again here, we have to confirm the conclusion. So plus root 3. Okay, so just we find the sign of these two quantities. So here we find that it is equal to approximately equal with calculator 0.1. So this is positive, and here minus 0.16 something. So it is negative. Okay, so in this case, we conclude that by the IVT, there is C, there exists C such that f of C is equal to 0. So the solution of our equation. Now, for the second part, we want to prove without graphing that the graph of the function y equal to sine x cubed had at least two x-intercept between 1 and 2.